So our first talk today will be given by Professor Sarah Sparrow, and Sarah will be talking about climate change effects on extreme weather and the impact of that on our infrastructure. Sarah's got a background in data-driven coupling of climate model output to impact models, and she's one of our course directors of our Energy MSc here in the Department of Engineering Science. She's also the program coordinator of CPDN, so this is climateprediction.net, a project which I'm sure many of you have already heard about. So, without further ado, I'm going to stand aside and introduce Sarah. Let Sarah give our first talk. So, over to Sarah. Thanks, Sarah.
Yeah, thank you, Wes, for the introduction, and thank you for inviting me to give this talk to you today. So I'm going to be talking about how we can boost energy system resilience in the face of future weather extremes. And the work that I'll be presenting is not just my own, but many kind of students and colleagues as well. And I'll try and point out key contributors as we go through the talk. So to start off with, if we think about extreme weather and how it may already be impacting our energy infrastructure, I thought it would be nice to start with a few sort of photographic examples. So here we've got a catastrophic failure of a wind turbine in high wind conditions. We've got a fire going through a solar farm. So that's affecting our energy generation. And then a windstorm causing kind of damage to the distribution network and fires to the transmission network. And one that I particularly like is the flooded substation, where you can actually see the flood defences that were put around to try and boost the resilience of this substation, but they didn't quite work. So we obviously need to learn something a bit more there. And then a sort of depiction of how in a warmer world we'll be have more reliance and need for air conditioning and space cooling, and we can see that, you know, the proliferation of air conditioning units in various countries. So to kind of frame my talk, I thought I'd give a schematic of the energy system, following from generation, transmission, distribution, and demand, and actually talk about some of the work that we've done in each of these areas with different kind of case studies. But before I go into each of the specifics, I think it's worth talking about the system as a whole. So if you think about one particular type of extreme weather event that we might experience, such as heat waves, then we can see that actually we might get impacts not just on one single part of the energy system, but on multiple parts due to one particular extreme event. So this is work that was carried out by an MSc student who looked at seven different large-scale heatwave outage events in Victoria in Australia. And you can see that we've sort of catalogued the impacts, and they've affected transmission, distribution, and generation assets. And the sort of key faults or issues that we've come up with is sort of thermal constraints on the lines, equipment failure, added risk because of fires and storm damage. The other thing is each of these areas we might have something that's very localized or specific to an individual place, where you've got a particular fault, where you have a particular asset that is located. But also you may have more broader, wide-scale, statewide impacts that affect the whole broader area. if we then go on to sort of analyse these a little bit more to think about, how does it affect us, the customers, we can think about the number of outages that we experienced, how many customer minutes were lost because of that outage, and we can also start to see sort of what part of the day we're generally seeing the outages occur. So we can see from this analysis that overloading and extreme weather were the primary drivers of the outages and also the severity of the extreme weather that we're looking at. And also we tended to get most of the outages in the sort of late afternoon, early evening period, which is sort of when people come home from work and they're, wanting to do something. I think it's also worth pointing out that, you might not get a heat wave in isolation. You might have other extreme events happening at the same time. So not only would we have a heat wave, you might have a drought happening at the same time, which will put added additional stress on resources and the operation of the systems, or you might have fires going on. And, this may add kind of compounding factors to make the sort of effects of these type of weather events kind of harder to overcome. So now on to the slightly more technical bit of how do we go about looking about this. We know that extreme weather, I've talked about in the current present day, how it is now. But really, we want to understand how climate change is going to affect this and what extreme weather might be in the future. We know it probably won't be the same as it is today. And if we're building things that we're expecting to last kind of, 20 or 30 years, then we need it to be kind of robust for those future weather changes. So the way in which we do this is we run climate model simulations and we simulate the world kind of as we currently have it now, but then we also include projected future climate change. So in this example, we might have a distribution of temperatures in green that we would expect during the current climate, and then we have a slightly different distribution under a warmer world. Now, if we think about our infrastructure, maybe it's got a critical component, and there's a particular threshold above which we start getting faults or issues. So really, we're not interested in the whole curve, but actually only the events that are at that threshold or worse. So we can compare the probabilities of the events in the future climate compared to the current climate and get what we call a probability ratio, or you sometimes might be referred to as a risk ratio, to see how much more likely or less likely a particular event might be with future climate change. The other way in which we can kind of formulate this figure, if you like, is to see how rare we think the event is. It's just exactly the same data, but just plotted a different way in terms of the return period. And here we can see that an event that we might be getting at the threshold that we'd see once every kind of 30 or 40 years has actually sort of become an event that we might see every 3 or 4 years with future climate change. And this is really important for us to understand if we're going to build an energy system that's resilient in the future. The other thing that we can get from these kind of figures is if we consider, say, a 1 in 50 year event, and this might be something which we're trying to build a particular piece of equipment to withstand as our sort of design specifications. What the 1 in 50 year event is actually changing. So what it would be under kind of current climate conditions may have a magnitude that is a lot less than we would expect under future climate change. So we need to understand what these levels are so that we can build things to be resilient to these thresholds. So if I go back now to my example and start with a sort of generation example, and this is work that was done by Sarah Abdelaziz as part of her DPhil work. And looking at UK offshore wind. So if we think about a wind turbine or a wind farm, how do they operate? Generally, we've got sort of wind speed going along the x-axis here and active power going up on the y-axis. So when the winds are low, we are not really generating anything because our turbine blades aren't turning, and so we have this sort of region of no production. Then we go through a ramp up in production as the wind speed increases in region 2 until we reach our rated kind of capacity for our wind turbine, which sort of starts off region 3. And then it's running at sort of full power until we reach perhaps wind speeds where we're going to have to turn the turbine off, otherwise we might be risking damage to our infrastructure. So we sort of fall off a cliff at the cutout wind speed. That means that we're kind of in this region 4. Then in what I've termed region 5, we may have another threshold, which is the sort of 50-year return period of wind speed, where we might actually be expecting to see physical damage to some of that infrastructure. So to try and make our life easier, we kind of looked at the exclusive economic zone around the UK, which is the shaded area, and split these up into north, south, and east, west regions of the UK. And rather than just arbitrarily draw some lines between these, we decided to kind of decide where the area should be based upon the shipping forecast regions, because they've got some kind of meteorological merit in terms of the types of weather conditions that you would be seeing. So if we go first to look at the low wind region, where we're not really generating any energy, we've got figures here that are showing various different cut-in wind speeds for the turbines. And if we start first with the maps on the sort of left-hand column, we've got current conditions, and then we've got kind of near future climate conditions and far future climate conditions. What's being plotted is the return period, and you can see that near the coast, you find it's much more likely that you're going to get these low wind events. They get less likely as you go to kind of lower wind speeds, but with climate change, it's becoming more likely that you will get these low wind events, and that's sort of summarized in these bar plots here for the different cut-in wind speeds. And you can see as well that although you've got this reduction or increase in the frequency of low wind events, they're less likely to occur in the north and west of the UK than they are in the south and the east of the UK. So if we think about on here, you might be able to see some green areas, and they are where we currently have our UK wind farm installations. We have quite a lot in the North Sea over to the east, and maybe we want to think about diversifying where we put some of these wind farms. If we now move on to think about the production regions of the wind turbine power curve, we can see that we're getting, with future climate change, we're getting increases in all of the regions because of monthly variability in our wind speed, and also increases in the seasonal variability of the wind speed. And this actually translates into the right-hand plot, that is showing a reduction in capacity factor in all of the regions with future climate change. So I should have said it's sort of blue is current, green is near future, and red is the far future conditions. also, that change is sort of depicted as a sort of an annual view, but we've got seasonal changes amongst these. So what I'm showing here now is the wind power density, and in this left-hand column is the wind power density. It's higher in the autumn and winter, and tends to reduce, reaching a sort of a low in the sort of spring and summer. Then the other two columns are showing the change with future climate change, and you can see that particularly for the summer, we're getting a reduction in wind power density. So we're expecting that we will be producing kind of less energy with future climate change because of these just the seasonality in the wind variation. So we need to think about how are we going to fill the gap that we might be relying on our wind turbines for producing power. Where are we going to get that power from? Are we going to store that power somehow in order to be able to use in these kind of low production areas? Then quickly kind of moving on to the other end of the high wind speed scenario. So here we're looking at the return time of wind gusts sort of exceeding 35 meters a second. And this time it's sort of less likely that we're going to see that in the kind of south and east of the UK, but we will see these sorts of things much more frequently in the northwest. With future climate change, this kind of variation between the sort of north and the south is going to be smoothed out slightly, so we'll see that we'll get an increased risk of these sort of wind conditions in the south and a reduction of them in the north. This actually looks fairly similar in the very high wind scenarios as well. This time I'm actually showing the maximum gust magnitude rather than the kind of return period. Again, it's sort of highest in the northwest of the UK, and again you're seeing this kind of change. So, perhaps the message from this analysis is really that we should be thinking about diversifying where we are siting our wind turbines on our wind farms to other areas, sort of expand it out from just being in the North Sea. I mean, there are some elsewhere, so that we can kind of try and make our energy system more resilient to these different changes in the weather that we might be experiencing. So now I'll move on to an example from the transmission system, and this is work by Eleanor McIndoe, who is an MSc student, and it's back to heat waves in Australia. So when we have extreme temperatures, then we may get sort of sagging of our transmission lines, and that increases the chance of risk of flashover and kind of physical equipment damage between our transmission lines. It might also kind of cause sparks and start fires, so it's something that we kind of want to stop, or operators want to stop. So obviously when you're passing current through a conductor, it heats up, so operators tend to reduce the power transfer capacity during high temperature events so that they can minimize the risks of this happening. And to achieve this, they kind of assign static or dynamic temperature ratings which indicate the maximum allowable current that you can actually pass through these transmission lines. So with any extreme event attribution study, we need to actually define what we term the event to be. And so in this case, we've defined it as the 6-hourly ambient temperature averaged over the area covered by the transmission network. So here we've got the transmission line locations above and the kind of grid squares that we're taking from the the climate model simulations, and then we can apply thresholds set by these static and dynamic line ratings. So now if we look at the return time plot, I should say this one is reversed from the others, just to check you're still following. So this time the more frequent events are further on the right and the less frequent events on the left. And you can see that for events that will exceed this 40-degree threshold, where we're actually having to take operations to our transmission lines, have changed from what would be about a 1 in 9 year event that you would expect to see that kind of behavior happening, to under only a 2-degree warmer climate that you would expect to see that kind of multiple times every year. And so this is actually kind of close on to a 10-fold increase that we'll be expecting. So this is obviously presents a big challenge to transmission network operators as to how they're going to deal with this. Quickly moving on then to a distribution example, and we're looking at this time flooding of substations. Back to the UK now, and this is work that's been done by a student, Dermot Leggett. So he was looking at flooding in Norfolk, and when you're talking about flooding, rather than just looking at precipitation or accumulated precipitation, you need to actually think about the river catchment areas, because it's where water will then end up pooling. So there are 6 different river catchments within Norfolk, and here we've sort of overplotted the primary and secondary substations, and I've also sort of noted where the 3 sort of main population centres are, just so that we can see. So when we come to think about what are our rainfall thresholds that we might want to be thinking about for our extreme events, I've got the three examples from 3 different catchments, and we wanted a consistent definition that was not really changing between the different catchments. So we picked the top 5% threshold that you would see for a particular river catchment area, and that's depicted by the red line. The kind of histogram is the distribution of rainfall that you would expect to see. The dashed blue lines are past historic events, and you can see that pretty much in all cases they are kind of more extreme than the 5% threshold. There are a couple the other side in Norfolk, but they're fairly close in Norwich. So we thought this was a reasonable threshold to be using to look at substation flooding. It's not all down to the meteorology, though, and there are other additional risk factors that come into play. If we look at UK power networks, they have the distribution operators within Norfolk, and they have several severity indicators. So there might be the number of transformers that you have on site. How many customers is that particular substation serving? Is it located indoor or outdoor? The other aspect that may affect how resilient our system is might be, where is our substation actually located? Is it relatively accessible? How far is it from the nearest road? How easy is it for us to get to? And then, as I said, the hydrology kind of comes into play in terms of the rivers, rather than it just being simply the precipitation that you might be experiencing. And so we can use the Environment Agency flood risk maps to give an indication of which particular kind of finer granularity areas are at most risk. And we can combine all of these together to get some sort of normalized risk factor. And so the large circles are the primary substations, and the small dots are the secondary substations. And you can see that really with the primary substations, they're located in pretty good places. Most of them are in low-risk areas, which is quite reassuring, so we perhaps don't have so much to worry about there. The same is not true for the secondary substations, and I'd like to point out that this is now on a log scale in that histogram, so you know, there's quite a bit more going on there, and we've got quite a range in risk values that we're seeing. So if we actually go back to the meteorology and the precipitation, how is this changing? I've just shown one example. So for a particular event threshold, we've got an increase in frequency that we're expecting to exceed that threshold with future climate change. And also the magnitude of, say, a 1 in 100-year event is increasing with sort of 2 degrees extra warmer climate. So this sort of harks back to that image of the flood station, the substation with the flood defences that were breached, and you know, perhaps they were using the wrong threshold when they were thinking what defences, the level of defences they should have in place. We can then combine all this information together to get a risk under future climate. And, you know, we can then start to see that we've got sort of localized centers as to where we're getting the most increased risk. And we've got a blowout of particular events that were happening in Norwich as to where individual substations were at higher risk. This is all useful information, but you know, how do we actually use it? How do we turn this into something that is going to be a decision support tool for operators and users? Well, we can start to think about, you know, this is where we know where these risks are highest, but we also know that substations will be under some maintenance cycle, and every so often they will be reinforced and things anyway. So we might start to think about, well, you know, if we've got a substation that's recently been upgraded, then we might want to prioritize that more for additional out of kind of maintenance cycle reinforcements in order to actually ensure that our energy system is more resilient. And that's sort of what we're showing here, is those top 95th percentile of those locations. So we can start to give some information that is really useful to operators to know practical information about what they should be doing. Then finally, very quickly, on to a demand example. And so Aubrey Taylor, one of our students, was looking at the heat dome in 2021 in the Pacific Northwest. And this is where you know, we were getting peak temperatures in sort of parts of Oregon in excess of 45 degrees. So it was pretty extreme. And if you look at what sort of deaths were experienced by the population, you can see that this is actually you know, not quite mapping, but because there are other factors involved, but you know, where you're getting the higher temperatures, you're also getting higher death rates. So I've highlighted a box around particular areas here because they're all served by the same Portland General Electric, and we could get the demand data from them. So if we take a look at what our daily mean temperature versus our demand is looking like, then you can see when we've got cold temperatures, our demand is increasing as we're wanting to heat homes. But as the temperature increases, then we are getting increased demand as well because we're wanting air conditioning. So we've highlighted on here particular days that corresponded to when the heat dome effect was in place, and also other heat wave days. And you can see that these are firmly correlated with the kind of highest demand situations that we can see that are going on. Now, we can also kind of translate this into the sense of a metric called cooling degree days, where you can look at the temperature above 18 degrees to see how much energy demand you might be expecting because of use of air conditioning. And this brings on to work that was done by Nicole Miranda and Jesus Lozana. And we're looking at the change in annual cooling degree days between 1.5 and 2 degree climate model simulations. These are 2 future climate scenarios. And if you look at the absolute change in cooling degree days, you can see that they're increasing a lot more in Africa and in the sort of tropical regions and sort of in Brazil. Whereas if you look at the relative change, then you're getting larger increases in the northern sort of high latitudes, and in particular places like the UK and Switzerland and Scandinavia, which have been sort of traditionally not very well adapted to heat scenarios. We're not used to having kind of air conditioning in our home. So this presents a big adaptation challenge for us in the future as to where we might need to be thinking about how we're going to install extra capacity. So I think I'm probably out of time, so I shall wrap things up there and just say that I hope that what I've shown you has sort of convinced you that climate change is impacting on all aspects of our energy system, and that through analysis such as this, we can help sort of understand what thresholds and where we need to target effort for the future, and in future development we need to sort of enhance the resilience of our energy system. So thank you.